Hey folks, welcome to my Turning Up the Heat review for the Unit 2 exam. Alright, and so in this packet I'm going to go through some of the most important things you need to know, and I'll do a little recap of all the sections. Going through most of the peppers, at least through the jalapeno, right? We got the bell pepper, the most fundamental questions, the jalapeno, the habanero, and the ghost pepper. I will do some ghost pepper problems. And again, we're just going to want to think about what we need to be ready for the test. So for the most part on the test, you need to get up to the habanero pepper in order for you to really be on track to get all of the similar questions right on the test. If you can get to the ghost pepper, that's a pretty good sign. I'm not saying the ghost pepper questions will not be on there, but generally the level of difficulty we're looking at is not going to be more difficult than the habanero, okay? But out of fairness to you and fairness to the process, I'm not going to be giving you details as to exactly what to expect on the test. For more info on that, you would probably want to talk to me about that in person, and we can kind of go from there, okay? So the ideas that are going to be covered on this are polynomial operations. That includes addition, subtraction, multiplication, basic factoring, some more advanced factoring, division of polynomials, okay, the remainder and factor theorems, which is and their application to factoring, okay, the rational roots or zeros theorem, graphing in the coordinate plane, analyzing graphs, all right, those kind of go together, polynomials and complex roots, and a few miscellaneous questions, okay? And again, for the most part, with a couple of exceptions here, we're looking at about 4 types of questions for each individual category. And again, I recommend you do the whole packet ideally, but the more you can complete, the more ready you're going to be for that exam. And keeping in mind that this exam, at least this year, is going to be the last major grade of the first quarter. All right, so I'm going to start by outlining some vocabulary, and we may either have talked about it in class at this point or may get to this in class, but if not, let's talk about these 4 fundamental vocabulary definitions here. Okay, so we have the degree of a polynomial, right, is the greatest power of x, or whatever variable you're using, right? Because sometimes I've used m's, I've used v's, I've used u's, I've used t's. Whatever variable you use, right, the greatest power of that variable, okay? So add or other independent variable, okay? Notice, and it's important to remember that it's important before you go off and say this, that your polynomial, okay, is in standard form. Remember, standard form is when you line up the variables so that they go from the biggest power to the smallest power. So let me give you an example. 3x cubed plus 2x squared plus x plus 1. This is in standard form, okay, because it's the biggest power, then the next biggest, and etc. This is not in standard form, okay? Not in standard form, because this power is smaller than this one. So to put it into standard form, I would just rearrange, okay? And now notice how the biggest power of x comes first. So that's really important to remember. When you see a polynomial, don't just go boom, it's the first one, because it's the degree means that it has to be in standard form, okay? It has to be looking at the biggest power of whatever independent variable you use, in this case x, okay? Now for the second one, the leading coefficient is the coefficient in front of the largest power of x, okay? So for example, here's my leading coefficient. Because the biggest power of x is 3, this number is in front of the 3. Here, it would be -3 because -3 is in front of the largest power of x in this case. And again, remember, if you don't use x's, it's whatever independent variable you use. All right, now for a little bit of vocabulary, okay? So we've got a couple key terms of vocabulary here. A polynomial of degree 2 is called a quadratic polynomial, okay? A polynomial of degree 3 is called a cubic polynomial, okay? And a polynomial of degree 4 is called a quartic polynomial, like quarts, like quarters in a gallon, cube, like x cubed, okay? There's also other things like degree 5 would be called quintic, all right? And then basically after that, my understanding is those kind of like official terms kind of start to fall apart. But it is important to know some of those classifications of various polynomials. All right, so I'm going to go ahead and get started. I do hope you guys notice on the back of this front sheet, there is a little space, okay, to do some important notes. And as you go, one thing that's a really good skill, especially as you guys think about college in the future, which is going to be, to be honest, closer than you think, thinking about taking the important ideas and summarizing them in your own words. If you can really build an effective sheet here where you take the big ideas, you boil them down, you synthesize them, you put them here, that's actually a really important skill that will help you in this class and other classes now and in the future. So again, I can't force you to do anything on this page, but I would definitely recommend you take advantage of that because I think that it will really be helpful for you. Okay, now I'm going to go ahead and I'm going to get started with polynomial addition, subtraction, and multiplication, okay? So here's the first part. When squaring a polynomial, you multiply a polynomial by what? Well, when squaring anything, you're multiplying something by itself, right? That's what it means to square, to multiply something by itself. So for example, 2x plus 3, that's 2x plus 3 times 2x plus 3. Okay, and then if I was to FOIL or box this out or whatever method you feel most comfortable with, that would be 4x squared, okay, plus 6x plus 6x, so it's a total of 12x plus 9, okay? That's the idea. So you're multiplying something by itself when you're squaring it. When you're cubing it, you're multiplying it by itself and then itself again, right? And that's what it means to cube anything. So cubing a polynomial isn't any different than cubing like 2 or 5 or 7 or -3 or x, except now there's multiple things that are being multiplied, right? It's not just the 2x, it's a 2x plus 3. Remember, you never distribute. I've been seeing a little bit too much of this. You do not write 4x squared plus 9. That's not right. You're not distributing the exponent, okay? It's not a number. It's an exponent, okay? So when you write it out like I do here, the idea is to get you to think about the whole multiplying by itself. Don't make that big mistake, okay? So let's go down, and here I'm going to take a look at some examples, okay? So let's find the sum, the difference, or the products. All right, so here, remember, all we're doing is we're combining like terms. So we're adding 2x squared plus x squared. It's 3x squared. We're adding -5x plus, okay, 7x. Okay, making sure, be careful when you're doing it in pen. And 4 plus -5, giving you -1, okay? So be really careful with your adding of negatives. That's sometimes where people tend to slip up. Okay, how about the next one? I kind of like do some arrows here so that we don't get stuck with the symbols there. So I've got, let's look through, okay? I've got an x cubed minus a 2x cubed. That's going to give me a -1x cubed, okay? I'm going to have a 3x squared minus -4x squared, so that's going to result in an adding. Okay, I'm going to have a 2x minus +5x. That's going to give me 2 minus 5. That's -3x. And then I've got -1 minus -4. Okay, that's +3. Okay, so again, we're just simplifying. We're combining the like terms. Now for a little bit of multiplication. And if you guys don't mind, I'm going to go ahead and box this one, okay, because I want to stay nice and organized here. So on my side, I've got 2x plus 3, okay? And then what I've got up here is I've got x squared minus 3x minus 5. Okay, so take a look. Make sure you got the same setup as me. Now I'll do it out. So 2x times x squared is 2x cubed. X squared times 3 is 3x squared. 2x times -3x is -6x squared. Again, observe the diagonal-like terms. Okay, that's a good sign. -3x times 3 is -9x. 2x times negative 5 is negative 10x. Again, we see the diagonality, okay? And then minus 5. I almost said diagonality, all right, for those of you who might get that reference. All right, so 2x cubed, that's going to chill. Okay, 3x squared minus 6x squared, it's negative 3x squared. Negative 9x minus 10x, it's negative 19x. And then negative 15 comes on right at the end. Okay, so we're just setting it up, we're boxing it out. Okay, last one, I'm also going to box this, right? This goes back to what we literally just talked about. So this is 3x minus 10 times 3x minus 10. So I get 9x squared minus 30x, okay? And then I get minus another 30x plus 100, okay? Oh, yes, plus 100, because negative 10 times negative 10. So I get 9x squared minus 60x plus 100, okay? Now that's why I tell people do not distribute the exponent, because when you distribute that exponent, you do get the 9x squared. You do get the positive 100, but look, you leave out that 60x squared in the middle, or 60x in the middle rather, that's leaving out a lot of important stuff, so you do not want to do that. Okay, now let's go down to the habaneros. So the habaneros are just a little bit harder. Here's some things that I noticed. One thing that makes it harder is things might be out of order. Another thing that makes it harder is you might not find a like term, all right, in the other one. Let me give you an example. Let's take a look at here. So negative 2x cubed, there's no x cubes in here. So I'm taking negative 2x cubed, and I'm not adding any x cubed, so it's going to stick. Now I've got 7x, and I'm going to add negative 13x. It's going to give me negative 6x. Now I've got a 3. I'm adding nothing to that 3, so I'm left with a 3, okay? And here's the thing. I don't have any x squared, so I'm going to add a negative 5x squared. Now here's the thing, you do need to make sure you put it into standard form in the end. So I'm going to go ahead and quick rearrange this. So sometimes it can be difficult, okay? And so that's why what my recommendation to you is going to be is look really carefully. Before you do anything, look at what you have on the left. Look at what you have on the right, okay? If you see things that are on the left that are not on the right, maybe think about inserting a 0x squared as a little mental note that you're going to have to remember that when you do the addition, okay? If you don't, though, please remember, turn that thing into standard form in the end. Maybe here's another strategy. Maybe cross out as you go, okay? Cross things out. Uh-oh, I still have a negative 5x I got to take care of. All right, now I'm going to do a similar thing down here. So maybe I'll do that, be a little bit vigilant in advance. Let's take a look. Okay, I got an x squared here and x squared there. Nice. But notice, uh-oh, no x cubed. So maybe I'll make a little mental note to myself, no x cubes. All right, x and a number. Okay, and there's no number over there. All right, let's take a look. So I've got 0x cubes minus negative 3x cubes. It's going to be 3x cubes because it's 0 minus negative 3. Okay. X squared minus negative 12x squared, that's going to be 13x squared. Okay. Now I'm on to the x. Negative 14x minus positive 5x, that's going to be negative 19x. And 9 minus 0, that's going to be plus 9. Okay, so you got to be really careful. You got to really take things step by step. All right, now we're in for a little bit of a doozy here, okay? So now we've got a situation where we got to really figure out what's going on. So we've got a trinomial times a trinomial, right? A 3 thing times a 3 thing. This is going to require a pretty big box. Boom, boom, boom. Almost like a little surrounded tic-tac-toe. So on the top, doesn't matter where you put them. X cubed minus 9x minus 7, 2x cubed, 6x, and 9. So let's take a look. Now here the diagonality is not going to be quite the same potentially, so let's see what happens. So I've got 2x to the 6th, negative 18x to the 4th, negative 14x cubed. Okay, I really love this because it lets you really take stock of everything. All right, now 6x times x cubed, it's going to be 6x to the 4th, okay? This is going to be negative 54x squared. Okay, why? Because it's x and x, okay? So immediately we might notice that the diagonal of this looks okay, but this doesn't. And if you think about why, I've got a cubes here, but I think part of the reason that we're running into this is because there is a little disparity, by which I mean there's no x squareds, there's no x squareds, okay? So that might be a reason there. And now, 7 times 6, that's negative 42x, okay? So the diagonal idea works sometimes, but it doesn't work all the time. And just because it's not happening for you doesn't necessarily mean you're wrong, okay? So don't let that get you down. All right, last one I got to do, okay, that's going to be 9x cubed. It's going to be negative 81 x's. It's going to be negative 63. All right, and now I'm going to combine my like terms here. So what I've got here is I've got 2x to the 6th. That's all by itself. Good. Okay, 6 minus 18, okay, is going to be negative 12x to the 4th. Okay, notice how there's no x to the 5th. That could happen. That could happen. Okay. Why is there no x to the 5th, though? By the way, think about it. To get an x to the 5th, I would need an x cubed and an x squared. There's no x squareds to make that happen. All right, now I'm going to do any x cubes in there. Yep, I got a 9x cubed minus a 14x cubed. It's a minus 5x cubed. Okay, I got a negative 54x squareds. I've got it now, negative 81 minus 42. We got to be careful. That's negative 123x, because if you do 80 minus 40, that's negative 120, and then 1 minus 2, that's negative 3, and then minus 63. I would say in general, this is going to be harder than what I would expect to see on the test potentially, but it is something you need to know how to do. It is definitely an important skill. Multiplying polynomials of any degree. Okay? All right, this last one, I'm not going to talk about that one. Okay? I think I'm going to leave that to you. This is one that was similar to one that was done on a previous quiz and which I recapped in a previous quiz video. So I'm going to do this one right here. So this one is going to be like this. Okay, similar idea, but look, it's a squared. So I'm just multiplying something by itself. So I've got x squared minus 3x minus 4. Okay, and on the other side, I've got x squared minus 3x minus 4. So again, I'll do this out. That's x fourth. That's negative 3x cubed. That's negative 4x squared. Okay, this is negative 3x cubed. Okay, this is 9x squared, because negative 3 times negative 3, x times x, and this is 12x. Okay, and then I've got negative 4x squared. I've got 12x. Nice, and I've got 16. Beautiful. Okay, this is why you can, again, not distribute the square. If you distribute the square, you get the x to the 4th, the 9x squared, and the 16. But look at how much you're missing. The bigger the thing that you're squaring is, the bigger impact you get when you forget to do the squaring, okay? Because you distribute it. So I do the x to the 4th. Good. Okay, combine the x cubes. I get negative 6x cubes. Make sure it looks like a cube. Okay? The x squareds, again, hitting that diagonal. 9 minus 4 minus 4, leaving me with 1x squared remaining. Okay, 24x and 16. So again, think about it like this. If I did that distribution, right? Yikes, that would be pretty tough. Now, not only would I be way off kilter, because the x squareds don't even work out like that, because these x squareds from doing the negative 3x times negative 3x, those are counterbalanced by these squares that are being distributed to other terms. So I'd be way off kilter. If I did the distribution, yeah, I'd get the ends right, but that's about it. Okay, so please, please, please do not ever distribute an exponent. It does not work like that. I get sometimes people want to do an exponent times an exponent. There are times you can do that. When you're squaring something that's a power already, yeah, there's times you want to do that. But please, please, please do not do that in this case. You're almost never going to be right. Like, the chance you're going to be right is extremely, extremely small. Okay, so again, this was recapped in a similar video, so I'm going to go ahead and move down to the last part. Write the equation of a quadratic, or I'd rather a quadratic. Now, here's the thing. This is actually not going to be a quadratic. This is a typo. This should say a polynomial. How do I know it's a polynomial? Because it's not a quadratic. Why? Well, a quadratic has to have a degree of 2. Remember that. But look, if I've got 3 zeros, I'm not going to get a degree of 2, right? That's not possible. So let's see what it looks like. It's going to be x minus 3, because 3 will make this equal to 0, okay? X plus 5, because 5 will make this equal to 0. And then finally, x minus 7, because 7 will make this equal to 0. Okay, and now I need to put it in standard form, so I do x squared. I'll start with this, x squared plus 5x minus 3x, so it's plus 2x minus 15. Okay, do the first one, multiply by the second, so I'll set up my box. So I've got x minus 7, x squared, 2x minus 15. Okay, set up your box, and let's do it out. X cubed, 2x squared, 15x, 7x squared, negative 14x. And this one's tough. 15, 30, 45, 60, 75, 90, 105. Okay. And remember, make it positive. Now let's bring it up. X cubed, 5x up, negative 5x squared, because it's negative 7 plus 2. Okay. This one, minus 29x plus 105. Okay. Notice, again, this is not a quadratic. This is a cubic, because its biggest power of x is 3. Okay, and when we get to graphing, what that means is, right, we're expecting to have 3 x-intercepts. 3, 0, negative 5, 0, 7, 0, and in each case, it's going to shoot through them. It's not going to bounce. It's going to go through, because each one has a multiplicity of 1, 1, 1. Odd multiplicity. Okay, so take a second, and if need be, go back, and then once you're ready, I'm going to move on. All right, awesome. So I'm going to go ahead and move to the next piece, basic factoring, okay? So let's begin, okay, with the bell pepper. When factoring, remember, and I've covered this in a few previous videos, first start by looking to take out a greatest common factor, or as some would say, a greatest common friend, okay? For after each step, okay, you need to go back to each factor and see if it can be factored more, okay? Because that's possible. And you really got to be rigorous going back and taking a look. Can I factor it each time? Okay. The sum and difference of cubes cannot be broken down anymore once you execute them, okay? What that means is that once I do a sum or difference of cubes, the quadratic that remains is one such that its discriminant is negative. And when you have a negative discriminant, it means no zeros, no real zeros. And when you have no real zeros, it means it cannot be factored. Now here we're talking about factoring over usually the integers, okay? So what that means is that when you're factoring over the integers, that means that if there are no real solutions, there will be no factors. If you were asked to factor over complex numbers, then that might be a little bit different. So keep that in mind. Usually when we say factor completely, we're talking about integers, real numbers, something like that. Okay, and mostly the integers. So let's talk about factoring completely here. So first I'm going to look here, and I'm going to see, okay, let's look. Is there a GCF? Remember, step 1, GCF. Yep, it's 3. Okay, then I look at x cubed plus 9. Can I factor that more? The answer is no, you cannot. You cannot factor this any further. X cubed plus 9 is as broken down as you can get it. And here's how I know. If you could factor this further, then there would be a number such that when I plug in for x, I get 0. Okay, but the cube root of 9 is that number, and it would actually be negative cube root of 9, right? However, that is not an integer. That's not something we're worried about. We are done here. Especially, you are not doing a sum of cubes because 9 is not a cube of any integer. So we're done. Okay, here. Oh, by the way, I didn't mention this. Rearranging and then taking out the GCF is called factoring by grouping. Okay, don't forget about that. Okay. Anyway, let's go back and take a look at this. So now I have factoring here, and that was actually an opportune time because now we're going to talk about factoring by grouping. Okay, remember that little technique? And I did do that in a previous video, so you may want to take a look at that. Okay, so here's what I've got. I've got x cubed plus 3x squared plus 2x plus 6. I'm going to go ahead and I'm going to set up my groups. Boom, boom. And I'm going to factor by grouping. So the GCF here, x squared, pull out an x squared, and I get an x plus a 3. Okay, then the GCF here is positive 2, and you get an x plus 3. Remember, sometimes you get some tricky negatives, right? The idea is that you always want these two things to be the same, right? Because then that allows you to do this. X squared plus 2, x plus 3, okay? That allows you to then take out the common x plus 3, and then whatever is remaining is that. Sometimes people like to put the x squared, the x plus 3 first. That's totally fine. That's totally 100% okay, because the order of factors does not matter. Okay, now I'm going to come down and see, can I do a further breakdown? Here I cannot because there are no real numbers that would make this equal to 0. Therefore, there are no factors within the real and integers. Here, I'm done. I cannot break an x plus 3 down. In general, no linears can be broken down, right? This is a linear polynomial because it's x to the 1, so I would be done there. All right, now I'm going to go ahead and move on to the last one in the jalapeno peppers, and I'm going to start one at a time. So let's look for a GCF. Do we see a GCF? There's an x in each one, and there's a 3 in each one. So I take my 3x out, and I have an x squared plus 3x plus 4. Okay, and to verify that, distribute 3x cubed, distribute 9x squared, distribute 4. Okay, because if I distribute the 4 and the 3x, I get the 12x. All right, now go through again. Can I break this down more? No, it's linear, done. Here, can I break this down? Well, do I know two numbers that multiply to 4 and add to 3? Well, in this case, I do not, because 4 is a positive number. Let's check our discriminant. So if I did b squared minus 4ac, that would be 9 minus 16, which equals negative 7. Negative discriminant means no real solutions. Therefore, this cannot be broken down any further than it already is. Okay, that's as much as you can break it down. Okay. Now, I put these in here to trick you guys because I want to see you thinking about at every step what's going on. So here's the idea though. Notice, what did I not do? Folks, I don't want to see you doing what x equals to. Is there an equation? No. If there's no equal sign, then x can't be equal to anything. When I say factor, I mean only break it down as much as you can. Okay? All right, now I'm going to go ahead and move on to the next ones. Some of these might even be a little bit silly here. Let's take a look. Okay, so here's what we've got, folks. We've got a little bit of more factoring to do. Again, first one, do we have a GCF? Yes. We take out the GCF. Here's what we get. Oh, look, it's the same one as last time with a similar GCF. That's somewhat of a little freebie for you, okay? So that's that. This one's a little bit harder. It's a similar factoring by grouping. Again, I take out a common y squared. I get y plus 2. This one's a little bit tougher. Okay, now you need to take out negative 2. Okay, and you get y plus 2. Okay, and again, you can check if that's right via distribution. One thing that we kind of got tripped up a little bit in class is we're like, okay, what the heck signs go in there? Is it a plus 2? Is it a minus 2? you got to think about the GCF of the second thing. If you see a negative in front of both of them, you got to ask yourself, well, do I need to take out a negative or a positive? What are you shooting to get? Well, look, I got a y plus 2 here. This has to be a y plus 2, or the factoring by grouping is not going to work, okay? So then I'm going to take out the y squared minus 2. I'm going to have the y plus 2, and I'll be good to go. Check again. Can y squared minus 2, can that be broken down? I mean, if you wanted to get cute with it, you could do y plus square root of 2, y minus square root of 2, y plus 2. That might be within striking distance, right? Because this is a difference of squares. But it depends. I think that's pretty valid, but something you want to think about. All right, the last one's going to be a little bit tricky. So go ahead and take a look at this one. Now, this one's tricky, right? So I want to do factoring by grouping. Here's the thing. 3 and 2 do not have a greatest common factor, except, of course, 1. So here's the problem. We've got to be a little bit more ingenious here. So, okay, let's think. Okay, so notice 3 and 12, they have a y in common and a number in common, right? A 3 and a y. Here, the 2 and the 8. So what I'm going to do is, this is a type 2 situation, okay? And again, I'm going to recommend, if this is something that's tricky for you, go back and look at the video on factoring by grouping. So I'm going to rearrange. I'm going to stick the 3y cubed. I'm going to stick that next to the 12y. And remember, the commutative property allows me to do this. And then I'm going to do the 2y squared, and I'm going to stick that next to the negative 8. So see how I did a little bit of a rearrangement. I flipped the 2y squared and the minus 12y. Now I'm going to factor by grouping. So I'll take out the GCF, and remember, it's a 3 and a y, and that leaves me with y squared minus 4. Okay? Now I'm going to take out a positive 2, because that's the only thing I can get there, and I've got a y squared minus 4. Okay, and I'm just going to do a little line here to cut that out. Then I've got, pull them together, 3y plus 2, y squared minus 4. Now, do I leave it? No. All right, let's take a look. 3y plus 2, can I break that down? No, it's linear, I'm done. Y squared minus 4, that's a difference of squares, okay? So you really need to be able to identify that. It's y minus 2, y plus 2. If you did y plus 2, y minus 2, 100% correct. Remember, the order of the factors does not matter because multiplication is commutative, but it's, again, something you want to think about there, okay? So remember, here's the idea. We're looking for a GCF. We're taking out those common factors. We're breaking down as we go, okay? I'm going to do one of the ghost peppers, and then I'm going to leave the other one to you. Remember, these are a little bit more challenging. I'm pushing you because I have a strong faith in you and I believe in you. And I think that if you can do these things with the ghost peppers, that's putting you in a pretty solid position. Again, having looked at the exam, I can tell you, if you can do this, I feel like you should be in pretty good shape on the test. But remember, it's not going to be easy. You've got to use every single tool at your disposal. So again, I look at this one. What am I going to look for first? It's going to be the GCF. So first, K's. There's a K in every single one. K, there's a K in here, a K in here, a K in here. So I can pull out at least a K. Is there a 3 in each one? Well, there's a 3 in here, a 3 in here, a 3 in here, and notice 3 plus 2 is 5, plus 4 is 9, so there's a 3 in all of them too. So I start by factoring out the GCF of 3K. So this becomes, you take out the 3, you get a 1, you take out 1K, you get a K to the 5th. Okay? You take out a 3, you get the minus 4. You take out a K, you get a K cubed. Okay? You take out a K, you take out a 3 from here, you get 27. Okay, 27 plus 27 plus 27 is 81. You take out a K, you get a K squared. 324, not as easy, but in this case, if I was to ask you this, you may have access to a calculator. Either way, you could get 108 times 3 is 324. K's are gone. All right, not an easy one. But here's what I noticed right away. I notice an opportunity. Whenever you see 4 things like this, I'm going to think about maybe factoring by grouping. And you know what? If you're wrong, that's okay. But here's the thing. You have a very limited set of skills here. I'm not going to throw you a problem if the skills you have in your tool belt cannot solve it, right? I'm not about that. It's not how I've ever been to you. I've never thrown you problems where the skills that I've taught you have not been able to solve them. So I'm seeing 4 things. I'm seeing 2 groups. Let's factor by grouping on this one. So I'm going to take a look. Now, I know, and you might have to know this, look, 27 times 4. Let's come off to the side. Let's do that. 27 times 4. Because I see a 1 and a 4. 8, 2, 10. Okay, 108. Because that would be an 8 when carrying the 2. Nice. So what that means is that maybe, just maybe, I could pull this one off. Okay, so I'm going to go ahead. I'm going to factor by grouping. I'm going to drop this big bracket in, so I don't want my brackets getting confused with my parentheses, okay? So here's what I'm going to do. The biggest k I can pull out of here, k cubed, okay? Now, k cubed times what is k to the 5th? K squared minus 4, okay? You can confirm that. Now, this is where it gets tough. This needs to be a minus, so I want to pull out a minus 27. I want to pull out a minus 27, and here's why I need to pull out a minus 27. Because, okay, this is a minus, the k squared is going to be a positive, but I need this to be a minus 4. So that's going to be a minus 4. That's how I know that I did it correctly. Okay, so here's what I've got. I've got a 3k. Now I pull the k squared minus 4, and then I pull the k cubed minus 27. Okay, now I need to go ahead and do some analysis. Am I done? 3k, good. K squared minus 4, nope. 3k, k minus 2, k plus 2, and then I drop the k cubed minus 27. Am I done now? Well, this one's good, this one's good, this one's good. K cubed minus 27. Uh-oh, that is a difference of cubes, right? Because my A value is k, my B is 3, right? Because k times k times k, k cubed, 3 times 3 times 3, negative 27. So I bring my 3k back, okay? I bring my k minus 2, my k plus 2, and now I'm going to do difference of cubes. So this one's going to be the same sign. Okay, then I've got k squared, opposite, always positive. Okay, so there's a real lot of stuff to break down there. Now I come back and I look again. Okay, can I break it down? No. Can I break it down? No. Can I break it down? No. Can I break it down? Nope. Look at this one. Now this one, we got to take a little look, but remember our rule with discriminant. Let's see the discriminant. B squared minus 4ac. So I'll come up here. 9 minus 4 times 1 times 6, that's 36. That's negative 27. The discriminant is negative. It cannot be factored further because it does not have real zeros. That is what the discriminant means, which means this is factored as far as you can get it, okay? So that's what we're doing. We're going step by step, okay? And we're breaking it down. We're starting with any GCFs. Then we're looking for other patterns we can do, okay? If it's something like this, you see 4 terms, that's assigned to factor by grouping. And then at each step, we look again. So I do the factoring by grouping, I get here. Am I done? Okay, wait a minute. I factor the squared, the difference of squares. I go again. Good, no, yep, uh-oh. And I just go step by step until there's nothing more you can do. I'm really seeing some positive improvement from people, really bringing down the GCF step by step. I personally recommend you take a moment to actually write out each step like I did, step by step, because that's how no things get left behind. Okay, so take a second if you need to, go back and take a look at anything, and then in a second I'm going to move on to the next thing. All right, so moving on. We've got factoring 3, the sum and difference of cubes, and what we call quasi-quadratics. I recommend, again, I do have a video on quasi-quadratics. I recommend you take a look at that if this is a particularly difficult part for you. Okay, so we got the sum and difference of cubes, or rather squares. This shouldn't say squares, this should say cubes. So the sum and difference of cubes formulas are as follows. Okay, so we've got a cubed plus b cubed is a plus b times a squared minus AB plus B squared. Okay, and then A minus B, A cubed minus B cubed is A minus B. Then we've got A squared plus AB plus B squared. Now, how do I remember this? It's using this idea of SOAP, okay, which means same, signs are the same, opposite, meaning these signs are opposite the sign that's between the cubes, and then always positive, okay? Same, opposite, always positive, okay? That's extremely important, okay? Same, opposite, always positive. All right, so we're going to look at a couple of examples. I have no additional notes on quasi-quadratics. Here's the only thing is you got to be really careful and go step by step. Again, remembering that I've built in some hidden GCFs in here. Okay, so we'll slide on down. We'll take a look at the first part. X cubed plus 27. It is a sum of cubes. So here's my A. It's X. Here's my B. It's 3. Okay, X times X times X. 3 times 3 times 3. Okay, so it's very similar to the one that I just did for the previous problem. So I've got X, same, opposite, always positive. Okay, now remember, this is going to yield a negative discriminant, so you're not breaking this down anymore. This one, quasi-quadratic, how do I know? The 3 is double the 6, or the 6 rather is double the 3, meaning it's quadratic because this is x cubed squared minus 8x cubed plus 12. So now it's like the x cubed is the quadratic. Some people say it's quadratic in x cubed. So here's what I do. I set up, just like it's a quadratic. X cubed drops in, x cubed drops in, and now I need two numbers that add to negative 8 and multiply to negative 12. Okay, that would be negative 6 and negative 2. And then I'd be up to the task of, hey, is this thing going to break down anymore? Let's see. Well, 6 is not a cube, 2 is not a cube, I'm done, okay? So remember, there could be differences of cubes built in there. You really want to look for that. Okay, next one, x to the 6 minus 4. Let's take a look. Again, it's a quasi-quadratic, and this is a difference of squares because this is x cubed squared, and this is 2 squared. Okay, so what I've got is x cubed minus 2, x cubed plus 2. Okay, again, I go through and look. Can I break it down? Is it a sum of cubes or a difference of cubes? It is not, because 2 and negative 2 are not cubes, which tells me that I am done. All right, now let's look at some more difficult ones. Factoring completely. Okay. So now I'm going to take a look through here, and this one's not as easy. Okay. My challenge is I need to look and see if there's any GCFs. Okay, so there's definitely a GCF here. Let's see what I could take out. Let's see. Could I take out a 2 from each one? I could try. And can I take out an x2? So let's see what that looks like. 2x. Then I pull an 8x cubed minus a 27. Why is that true? Because 27 times 2 is 54. And then I put on the x. And then x times x cubed is x to the 4th. 2 times 8, 16. This one's good. Is the second one a difference of cubes? It is, because look. 2 times 2 times 2 is 8, and x times x times x is x cubed. And then b is going to be 3. So this is a difference of cubes, folks. So let's pull out the difference of cubes formula. Remember, AB is 6x. So I've got 2x. I've got, first of all, I set up my 2x, same. Okay, now this is where a lot of people get tripped up. I don't want to just square the 2, I want to square the 2x. So 2 times 2 is 4, x times x is x squared. Okay, then I drop my opposite sign. A times b gives me 6x, and then always positive for the 9. Remembering, this is not breaking down. Again, 36 minus 4 times 9, that's already 36. So when I multiply the 4, I'm going to get way, way, way negative on that. No way this has a positive discriminant. That's not going to have any real solutions. I'm done right here, okay? So again, you always need to be looking for room to take out those kinds of GCFs and stuff like that. And anytime you see like a cube, especially when there's two numbers, you got to ask yourself, is this a difference of cubes? All right, coming forward, we got this. Is there any GCFs? There is. There's a 2 in all three of these. So that will become a b to the 6th minus 4b cubed minus 8. All right. So what sets me off here is the idea that, I've got an 8. Darn, can I factor this anymore? Well, oh, this is not an 8. My apologies. This is a 12. That makes it a lot more sensible. Okay, so now can I factor this anymore? Because originally I was like, I don't know. This one, definitely. So I pull my 2 out. I need 2 numbers here, and I've got b to the 3rd and b to the 3rd because this is quadratic and b to the 3rd, or b cubed. Let's see. 2 numbers multiply to negative 12 and add to negative 4. Okay, I think I know. Negative 6 and positive 2. Negative 6 times positive 2, negative 12. Negative 6 positive 2, negative 4. Beautiful. Okay, now I go through. Can I break the 2 down? No. B cubed minus 6. Okay, is it a difference of cubes? Let's take a look. Cube. Nope, that's not a cube. 2's not a cube. I'm done. That's as far as I can go here, and I move to the next part. Okay, this part right here, I'm going to go ahead and I'm going to try and do a little more breakdown there. So I'm going to take out a GCF of 4. Okay, that's going to be x to the 4th minus 4. I come back again. Can I break down the 4? No. X to the 4th minus 4, that is quadratic, and x to the squared. So that would be x squared minus 2, x squared plus 2. Okay, and that's as far as I can get with that. So then I look, x squared minus 2, can I break that down? No, it's not a difference of squares. Sometimes you could get at something fancy like that, where this is actually something to the 4th. Maybe you get some kind of funky little breakdown where this would also be a difference of squares. But in this case, 2 and negative 2 are not squares. So I'm done right at this point right here. All right, on the last one, I'm not going to do all of these. I'll do maybe 1 or 2 of them. This first one, I'll tell you the idea is you want to take out a GCF, and then it's probably looking like it's going to be some kind of factoring by grouping, okay? Here's what I notice. One thing I notice is that there's a GCF. I notice that they all have an x in them, so I've got to take out at least an x. I then notice they all have a 4 in them, okay? I believe, and I could be wrong. So there's at least a 2 in them. You know what? There's not a 4 in them. There's a 4 in the 108 because the 8 is divisible by 4. There's a 4 in the 32 and a 4 in the 16, but there's not a 4 in the 54. So this one might be tough. I can definitely see at least a 2 in them, so that's going to require some factoring and some careful thinking. We've done one similar, so I'm going to move on, and I'm going to take a look at 3x to the 17th minus 243x. So 2 plus 4 plus 3, well, that's 9. So they're both divisible by 3, because 3 is obviously divisible by 3, and there's an x in both of them. So by the way, the difference here is that here we're going to try to find the x-intercepts. So if I take a 3 out, I get a 1, and I've got to get an x to the 16th. That's what I got left there. 243, not easy. Well, here's the thing. 3 goes into 24 8 times. 3 goes into 3 1 time. So I've got x to the 16th minus 81. Can I break this down more? Yes. 3x. This becomes an x to the 4th minus 9. This becomes an x to the 4th plus 9. Okay? So this one would be tricky, right? And when I think x-intercepts, I think, how about we focus on integer x-intercepts, right? Because this is definitely going to have like the fourth root of negative 9 that actually doesn't have a solution, right? There's no number times itself, times itself, times itself. It's going to give you a negative 9. This, let's try for a little breakdown. This is also a difference of squares. X squared minus 3, x squared plus 3, x to the 4th plus 9. Okay, so here's the thing. No real solutions on that. Why? Because remember, if I was to solve this for 0, because this is equal to 0 now. If I was to solve this for 0, right, I'd get x to the 4th equals -9. There is no number that times itself, times itself, times itself, right? This is what I'm saying. There's no number that's real that's going to make that true, because there's no way to multiply over and over and over again and get a -9. If you choose a negative, when you multiply it over and over and over that many times, it becomes a positive. If you do a positive, it's going to be a positive. And if you do 0, well, that's going to be 0. So that's going to have no real solutions. Similarly, it depends if I want all real numbers. In this case, let's say I want real numbers, right? Because if I want complex, it's going to make it a little bit trickier. This is going to have no real zeros either. And I know that because x squared equals -3 is going to be the square root of 3i and the negative square root of 3i. This one here, this is going to be plus or minus the square root of 3, and this is going to be 0, okay? It's as far as we can go. But the idea is this is a quasi-quadratic, and I guess if you want to do this one, you could do plus or minus the square root of 3i, okay? But again, the idea is it's a quasi-quadratic. Okay, finally here, let's take a look. So here, I see a 25, I factor out the 25. I see an x, I factor out the x. This becomes an x to the 8th minus, okay, let's take a look, 4. So this again is a difference of squares. 25x, this is x to the 4th minus 2, x to the 4th plus 2. Again, x to the 4th plus 2 is going to have no real zeros. X to the 4th minus 2, oh, that's tricky. That would be the 4th root of 2. Not going to be much of an integer. So you get x equals 0. And then you'd get, so this would be x to the 4th minus 2 equals 0. So x to the 4th equals 2. So x equals plus or minus the 4th root of 2. And I think that's way beyond what I'm going to ask you to be doing on the test. But this is the idea. Factoring and setting it to 0 and knowing that by what we might call the zero product rule or the zero product property, that every one of the factors, or at least one of the factors, has to be 0 for the whole thing to be equal to 0. Okay, so take a moment, if need be, go back and look at this, and then I'm going to go ahead and move to the next part. All right, so moving on now, we're going to polynomial division. All right, polynomial division. So remember, there's 3 methods for dividing. There are polynomial long division, okay, the traditional method. We have the box method in reverse. That's like doing it like a puzzle. And then we have synthetic division, okay? And I'll add that in there, synthetic division. Okay, those are the 3 methods we've learned. Now, you can never use the third method with something like an x squared or x cubed or anything that's not just a plain old vanilla x. And remember, if there's a number in front of the x, we've ran into that problem where it's like, ooh, I don't know about that. That's not going to work out so well. So I would really caution you when using synthetic division, unless it's just like x minus something or x plus something, just like that. That's a good time to use the synthetic division when you want that quick division. All right, so I'm going to take you through on this one the jalapeno and the habanero. I'm going to start by saying, as a disclaimer, the ghost pepper is way, way, way hard, and I don't think, personally, it's something worth getting wrapped up in. So if you are really, really struggling on the ghost pepper, I would say you may want to make sure that you've looked at some other parts of the packet and you don't get too wrapped up in that. Okay, so before I move on, remember, if you divide by x plus 5 and you get a remainder of -3, don't forget to write the remainder as -3 over x plus 5. In other words, it's always the remainder over the thing you're dividing by. All right, so here I go. I'm going to divide using any method. I'm going to show you the synthetic method, and I'm going to show you the, maybe the box method. Let's see. So, n plus 10, and that's being put into n cubed plus 11n squared plus 7n minus 37. I set up my bus driver. I've got 1n cubed, I've got 11n squareds, I've got 7n's, and I've got -37. Okay, here we go. So I bring down the 1. 1 times negative 10 is negative 10. Add them through, get a 1. 1 times negative 10 is negative 10. Add them through, get a negative 3. Negative 3 times negative 10 is 30. Add them through, get negative 7. That means my answer is x squared plus x minus 3 plus negative 7 over n plus 10. And I'm sorry, I really should be using n's. So it's n squared plus n minus 3. Okay, make sure you do use the variable you wrote it in. I'm personally used to using the x, so you can see that's even something that throws me off sometimes. But I would say use the variable you started in, okay? All right, now on to do the second one, okay? So here I go. I'm going to box this one. Ready? So I've got my w minus 2 on the side. So this has to be a w cubed. So this needs to be a w squared, so that w squared times w is w cubed. Then I bring this one down. That's 2w squareds, because w squared times negative 2. I need to have 4w squareds in my answer, so this needs to be a 4w squared. All right, because that's got to be a 4w squared, this has to be a 4w, so they multiply out. Then this has to be negative 8w's. Then this has to be a 9w, so they add up to positive 1. Okay, this has to be a plus 9, so they multiply to 9, and this becomes a negative 18. And now I need to know, well, I'm supposed to get a negative 13 in my answer. Darn. So what do I need to add to get that to happen? So what that means is that my answer has to be remainder of 5, because negative 18 plus 5 gets me back to negative 13, which is where I need to be. Okay, so there I get my answer. So remember, the difficulty with the box is good because you don't have to worry about some certain things, such as the nitty-gritty of the synthetic, but the box is tough because it's sometimes tough to interpret the remainder. But you got to ask yourself, I have this remainder, what do I need to do here to get back to the number that's actually in the problem? All right, now I'm going to go down to the habanero. Divide here using any method of your choosing. So here's the trick part here. Notice j squared. That means synthetic is off the table. I'm not going to do synthetic on this one, okay? That's not what I want to do. So here's what I will do. I'm going to think about how about I do the traditional on this one. So here I go. J squared plus 1 goes into, let's check for, oh, I got a missing exponent, so let's check for that. So I've got 2j to the 4th plus 0j cubed plus 3j squared minus 8, this should say a j, plus 21. And if there's any typos in this, I'll try to fix those up after I do the video. Okay, so here I go. Now, you always have to insert the 0 because that will always throw you off in any particular situation right there. All right. So I do j to the 4th over j squared, 2j to the 4th rather, and I say, okay, what times j to the 4th gives me what times j to the squared gives me 2j to the 4th? That is 2j squared. So I put that there, then remember I come through, I get 2j to the 4th, okay, plus 2j squared. These cancel, I get negative 2j squared plus, this is a squared, so that doesn't go there, it goes here. So I get j squared, see, that's where this can get tough, right? Because you want to put it where it goes. J squared minus 8j plus 21. All right, now remember, in this case, you may get to a situation where you have multiple things left over. J squaring as a denominator is another reason why the box method can get tough, okay? So now, let's take a look. J squared over j squared is, okay, no j's, right? See, that's the trick, right? There's no j's in this one, right? Because what times j squared equals j squared? No j's, right? Yikes. Because look, we had to do the j squared times the j squared there. That's a tricky one. And so the issue is you got a lot of stuff that's missing in this case, right? Because we had the j fourth, those canceled pretty easy. But now we're stuck with, we had no j cubes. That's all right. There's no way to work that out, meaning that there's no j's. Because there's no j cubes, when I do the division, I get no j's. But now when I do the j, what times j squared is j squared? It's 1. J squared comes in. The 1 comes in. And what I get is negative 8j plus, so this is 20 plus negative 1, positive 20. Okay? So what I get for my answer is, and I'm going to come right over here, I get 2j squared plus 1 plus negative 8j plus 20 over j squared plus 1. Okay? The reason there are j's in my remainder is because of the thing that's being divided into. So I'm putting the j squared into the j fourth stuff. Your remainder, the degree of your remainder, which in this case is 1, will always be less than the degree of the thing you're dividing by. So that means that either I could have numbers left over or I could have j's and numbers left over. Here, the thing we were dividing by had a degree of 1, meaning the answer had to have a degree, or the remainder rather, had to have a degree of 0, which is what we had, right? Because there's no x's in it at all. So that's one thing to look out for. All right, that's a tricky one, and I'm going to say this. At least for this unit test, I do not believe you're going to have to be dividing by something squared, but no promises as to whether that will or will not show up in the future. This last one, because I'm getting a little bit fatigued with the division at this point, I'm going to do a little bit of synthetic. Wonderful. So I'll drop in my negative 2, box that out. I've got 1x to the 6th plus 0x to the 5th minus 3x to the 4th minus 8x cubed plus 0x squared minus 1x, or s I guess we're using in this case, plus 2. The x and the s, remember, don't make a huge difference. The important part is you know what you're leaving out. Okay, so the 1 comes down, I get 1. And remember, just double check. X to the 6th, no x to the 5th, 3x to the 4th, negative 8x s squared, negative 8x cubed, rather, 0s squared, negative 1s plus 2. Okay, it's always good to double check your bus because if you make mistakes, if you leave out zeros, remember that's one of the big things that throw people off. All right, so the 1 comes down. The 1 times negative 2, give me negative 2. Adding through, give me negative 2. Multiplying gives me 4. Adding gives me 1. Multiplying gives me negative 2. Adding gives me negative 10. Multiplying gives me 20. Adding gives me 20. Multiplying gives me negative 40. Adding gives me negative 41. Multiplying gives me positive 82. Adding gives me 84. So what my answer is I've got nothing. So I've got, I like to work backwards. 41, 20x, negative 10x squared. Then I've got 1x cubed, right? Because I've got x squared. So these are the nothing. This is the x squared, x cubed, x to the 4th, x to the 5th. Okay, and then I tack on my remainder. And remember, we're using s's here. Again, resisting that temptation to use x for everything, unless maybe you want to do it in pencil and then switch it over in the end. But remember, if you start with s's, you have to end with s's. So we have s to the 5th minus 2s to the 4th plus s to the 3rd minus 10s squared plus 20s minus 41 plus 84 over s plus 2. All right, so a lot of rigor, a lot of stuff you got to think about. But again, we want to be able to know how to multiply anything by anything. I would say in this case, habanero, probably more difficult than the exam. I would say jalapeno, definitely fair level for the exam. And of course, these are fundamental concepts, so we definitely have to know those. Okay, so take a sec, and again, don't let the habanero get to you. Please do not let the habanero get to you. And in fact, the ghost pepper, I just want to really briefly say, when you factor completely, in this case, this could end up being one of the factors. In this case, don't worry about the h minus 1. Just factor the stuff on top, and don't worry about it because there is a whole nother section of this packet on factoring. So please don't let the habanero or the ghost get to you. That's something I may be revamping in the future for sure. Okay, so now I'm going to go ahead and I'm going to move on to the remainder and factor theorems. Okay, those are extremely important when we talk about factoring, okay? So the remainder theorem says that when you divide a polynomial p, okay, by a polynomial x minus a, the result is the same as plugging a into the polynomial. In other words, to find the remainder of p over x minus a, you plug a into the polynomial p. That's all you do. You plug in a. If you get 2, that means when you divide by x minus a, the remainder is 2. That's a really good SAT question. Definitely a fair test question, just from like a fundamental understanding perspective. Okay? Second thing, the factor theorem says, okay, that if p of a is equal to 0, well, think about it. If you get a remainder of 0, if you plug in 0a and you get 0, that means when you divide p over x minus a, you get a no remainder, which means that to get no remainder means that x minus a is a factor of p. Okay? This is technically considered a corollary. The factor theorem is, since it's based on the remainder theorem, not something you need to know, but it is important. It's like cool to know. It's not invaluable. It's not valuable. So I guess I should say, you know, some people could consider it like definitely something like technically wise you probably want to know. Anyway, we can easily find the remainder using synthetic substitution, okay? Which is synthetic division, but then you just use the remainder and that's what you got out of it. All right, so first step here, determine the remainder without dividing, okay? No dividing allowed. So here's what I do. I'm just here, x minus 1, I'm plugging in 1. Here, I'm not going to use synthetic because plugging in 1 is pretty easy. If I plug in 1, that just becomes a 2. If I plug in 1, this becomes a 3. If I plug in 1, this becomes a 2, and so on. Okay, so 2 minus 3, that's negative 1, negative 3, negative 2. So that would be the remainder there. Here I'll use synthetic substitution because this is a little bit more involved. So I've got 1, 5, 0, negative 7, 12, 1. Again, notice no x cubes. So I drop the x1, I get a 1. Multiply, I get a negative 1. Adding gives me a 4. Multiplying gives me negative 4. Adding gives me negative 4. Multiplying gives me 4. Adding gives me negative 3. Multiplying gives me 3. Adding gives me 15. Multiplying gives me negative 15, right? Adding gives me negative 14. That is my remainder. You could add this up as well, right? But the only thing that's tough about this is that you're going to get some wonkiness with those negative and positives. So, right, if the power rather is odd, it's going to end up being a negative. If it's even, it's going to be a positive. It's going to be all kinds of nuts stuff going on there. Negative 1 is just weird like that. All right, so, but that's the idea. Plugging in the opposite, essentially, of this number tells you what you're going to get when you divide. And actually, I just even did the whole division for us, right? All right, now I'm going to use the remainder and factor theorems to find the factors of x cubed minus 21x plus 20. So here I go. Now, I'm going to choose some easy numbers, and I'm going to do a guesstimate. I don't know. Let's guess 1. I don't know. Is 1 a factor? Yep. Look, 1 minus 21, that's negative 20, plus 1 is 20. Okay, so the first factor is x minus 1. So I'm going to do this. Ready? I'm going to take out a 1. And now I'm going to do 1x cubed, no x squareds, minus 21x's, and 20. Okay, because there's no one in the x squared part of the bus today. So I bring down the 1, I get a 1. Multiply by 1, I get a 1. Add 1, I get a 1. Okay, multiply by 1, I get a 1. Add, I get a negative 20. Multiply by 1, I get a negative 20. Add through, I get a 0. Exactly what I was expecting. So we break it down. This becomes, and I'll just move this down here, x minus 1 times x squared plus x minus 20. And now I factor the quadratic. It becomes x minus 1, x plus 5, x minus 4. That's the exact idea behind that. Okay, now I'm going to move on to the final one, which is the ghost pepper. Again, definitely very difficult, so we'll see what we're going to do here. All right, so we're going to use the remainder factor theorem and any other skills at our disposal to factor completely. The first thing I notice is there is a GCF, so let's go ahead and take out the GCF first. The GCF is x. Okay, this should probably say x squared. And now I have to really think about what the factors of this guy are going to be. So I have to be using a calculator most likely. I could try and see if I get lucky with the specific like values. We know from the rational roots theorem that's probably going to be one of, a factor of 168. But I think for this one, the idea is we're just going to go through and we're going to look through it piece by piece. What I'm going to tell you is this. I would say don't get too wrapped up in this one. I'm not going to go into the nitty-gritty about what we would check. I would try to check maybe 2, etc. But again, I wouldn't get too wrapped up in this one. I'm not going to get wrapped up in it only because I see this as more of a challenge and I want you to try that challenge on your own. I'd be happy to check in with you about it, but just for time's sake, because we're already going pretty long, I'm going to move on to the next one. But remember, thinking about those common ideas like the GCF. Okay, speaking of which, now I'm going to move on to the rational root theorem on this one, okay? So the rational root theorem says that if m over n is a 0 of any polynomial function p of x, meaning that, right, you plug it in, you get 0, then m is a factor of the constant coefficient, and n is a factor of the leading coefficient, okay? And most likely the leading coefficient is going to be 1, and that's going to make the process a little bit easier for us, right? So remember, the constant coefficient is the coefficient with no x's in it, while the leading coefficient is the coefficient in front of the largest power of x. Do not forget to put it in standard form. Now I'm going to come through and we're going to look at all the possible zeros using the constant coefficient, okay? So I look at 12. What are the factors of negative 12? I have plus or minus 1, because 1 goes into anything, as does negative 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. That's the idea. Okay, you're plugging in numbers over and over and over. You're looking for the factors, and there's where we go. What that means is that there are this. One of those, at least up to 3 of them probably, have got to be factors of this guy. How about 15? So 1 goes into it, so plus or minus 1, plus or minus 3, because 2 doesn't go in, 4 doesn't go in, 5 goes in, okay? 6 doesn't go, 7 doesn't go, 8, 9, 10, 11, 12, 13, 14, 15. So you should always include 1, and you should always include the given number, because 1 goes into anything, and every number is divisible by itself. Okay, so let's try to use the rational root theorem here to factor completely. Okay, so here we go. Remember, on a test, you are going to have to build your own synthetic division tables. I will not provide that for you. That's extremely important to know. Okay, so here I go. I'm going to start with 1, 1, negative 8, negative 12. Okay, over here, I'm going to do 1, negative 9, 23, and negative 15, because I'm going to plug in the coefficients. And remember, the synthetic division table makes it nice and clean for us. okay? So I can tell by looking at it, I just get this funny feeling that 1 will not work on the first one, all right? However, what I did notice is this. I noticed that, right, because 1 plus 1 is 2, that's not going to work out. Maybe I'm going to try, let's see. I'm going to think about what would be a strategic one. Maybe I'll try, let's try, I don't know. Let's try 2, 3, 4, and 6. Okay, and maybe one of these will work out to be a nice positive, or get me a 0. And if I don't, I just keep going. So, okay, so in each case, I'm going to bring down. Bring down. 2 times 1 gives me 2, plus 1 gives me 3. 2 times 3 gives me 6, plus -8 gives me -2, and 2 times 2, that gives me -4, -16. Nope. All right, no big deal. Now I do 3. Okay, 3 times 1 gives me 3, plus 1 gives me 4. 3 times 4 gives me 12, plus 8 gives me, let's see, 12, negative, let's see, right, 3 times 4 gives me 12, plus 8 gives me +4. Okay, I think I see something good in this one. Okay, in that case, 3 times 4 gives me 12, plus 12 gives me 0. Okay, now let's see if that actually works. What if I plug in 3 here? 3 times 3 times 3 is 27, plus 9 is 36, minus 24 is 12, minus 12 is 0. Okay, so that's going to work. So here I go. Now, I set up my x minus 3, and then I'm going to set up my x squared plus 4x plus 4. Okay, and now I go through. Can I factor this? No. Can I factor this? Yes. This is going to be x plus 2, x plus 2, and technically we should write that as x minus 3 times x plus 2 in parentheses squared. Okay, remember, once you get a 0, if you keep going and you keep getting more zeros, remember, someone in class asked me that. You're not wrong, it's not invaluable. What would I do? So let's say I had plugged in -2. I should have gotten 0. What I do with that is I then use that later on down the line, because if I had gotten a squared and I'd gotten another 0, well then I know that that associated number has to go with a factor of whatever is remaining, and then that would be helpful to help break it down even more. How about over here? So I know it's got to be a factor of 15, -15 I suppose, so I've got 1, 3, 5, and 15. Let's see if I can get lucky on this one. I'm trying to think about what would I want to plug in. Maybe I'll try to plug in 1 first and see what happens. Maybe I get lucky. So 1 comes down, I get 1. 1 times 1 is 1, plus -9 is -8. Okay, -8 times 1 is -8, plus 23 is -15. -15 times 1 is -15. Plus -15 is -30. Darn. And if I actually come up and look here, 1 minus 9 is -8. Plus 23. All right, I'm going to double check my work here. Let's just double check my work real quick. Because let's say I come up here. 1 minus 9 is -8. Plus 23 is 15. Minus 15 is 0. So did I make a mistake? That is the question. Let's see. So 1, add, you get 8, you get 15. No, okay, so let's see if I can find another one. What other numbers could I try here? What if I tried 3, 5, and 15? What would I get? Oh, here's my mistake. I finally found it. 23 plus -8, that's positive 15. And then I add and I get 0. But I'm going to try a couple other ones just to show you. So bring down 1. Because you know what? What if you had not caught that? You'd have to try another one. So bring down 1, I get 1. 1 times 3 is 3. plus negative 9 is negative 6. 3 times negative 6, that's negative 18. Negative 18 plus 23, that is 5. 5 times 3 is 15, plus 15 is 0. Perfect. What if I try 5? Bring down the 1, I get a 1. Times 5, I get a 5, that becomes a negative 4. Negative 4 times 5 is negative 20, that brings me a 3. Wow, look how lucky I got. 3 times 5 is 15, and then I get a 0. Wow, look how lucky I am. So I got a lot of different choices. But the thing is, you got to be really careful, and I would try to say, especially if you have this on a calculator section, try to do as much as you can with the calculator, because then you avoid these like confusing things. I got stuck with that for a second as well. So I'm gonna go ahead, I don't know, I'm gonna choose the x plus, let's say I had not seen the x plus 1 or x minus 1, and I went with the x minus 3. So I'm gonna go with this one. X minus 3, I got x squared minus 6x plus 5. And now I go, okay, this is done. Can I factor the second? X minus 3. And I get x. Let's see. So adding to 5, adding to negative 6, multiplying to 5. That'd be a minus 5 and a minus 1. And then I would be done. Now remember, there's multiple different ways you can do this. So don't get yourself down on that. All right, last but not least, I'm going to do this one. This one I think is pretty doable. Hopefully we will find some factors that'll work here. This is more along the line, I would say you probably would not have a number bigger than 12. I'm not looking to hit you with something super big where it's super hard to get the factors. That's not what it's about. Remember, there's a lot of stuff I want to ask you, and I care more about your ability to use it than to break down big numbers, okay? So here I go. I'm going to now come in and I'm going to look at 4, and I've got plus or minus 1, plus or minus 2, and plus or minus 4. Okay, so that's what I got to worry about. So I'm going to try to see what I can do here. I'm going to need to make a table. I'm looking through and I can see 1 might be a good idea. I've got some pretty small numbers, but I don't know. So let's see what I can do. I'm going to try 1, I'm going to try 2, I'm going to try negative 2 and maybe 4. Let's see what happens. And if none of those work, that's okay. So I've got 1x to the 4th minus 2x cubed minus 3x squared, 4 x's, and a 4. So let's bring it down. 1, 1, 1, and 1. All right, so 1 times 1 is 1 plus negative 2 is negative 1. Negative 1 times 1 is negative 1. Plus negative 3 is negative 4. Negative 4 times 1 is negative 1. Plus 4 is 0. 0 times 1 is 0. Plus 4 is 4. So 1 is not a factor. 2. So 2 times 1 is 2. Plus 2 is 0. That one will make that easy. That'll become just a 3. Okay, because 0 plus 3 is 3. Negative 3 times 2 is negative 6. Plus 4 is negative 2. Negative 2 times 2 is 4. Negative 4, rather, plus 4 is 0. Good news. So what we do is I'll break it down. And so far, I've got x minus 2 times x cubed. 0x squared. Maybe I'll keep the 0x squared there for now. Minus 3x minus 2. Now I need to look at the factors of 2. I'm not going to look for 1, because if 1 did not work here, 1 is unlikely to work there. Because if 1 is a factor of this, then 1 is a factor of that. So I'm not going to choose 1, but I'm not going to choose, I could choose 2 again. Let's see. You know what? Let's choose 2 again. You never know. I'm seeing from a quick inspection that 2 might actually work. So now I'm going to go again. I'm going to not choose 1 because I know 1 is not going to work. Remember, if 1 had worked here, 1 would have worked here, because all the factors of this have to be factors of this because they're equivalent, right? So I'm going to choose 2. I'm going to choose negative 2. I'm going to choose negative 1. Okay? So let's look at that. We got 0, 1 rather, 0, negative 3, negative 2. Okay, so I go bring the 1, 1, 1. 2 times 1 is 2. Plus 0 is 2. 2 times 2 is 4. That becomes a 1. Okay, and that becomes a 0. Nice. So I've got x minus 2 times x squared plus 2x plus 1. Let's bring down the other x minus 2. And now this over here, can I factor it? Yes. Let's try not to use the rational roots if we don't need to. This is x plus 1 and x plus 1. So this is actually cool. This is x minus 2 squared times x plus 1 squared, okay? So the idea is we're using the rational roots theorem. We're starting with the factors of the constant, lining them up, plugging them in one at a time, because one of those, provided that this is a 1, one of those almost certainly is going to be it. And even if, by the way, this is not a 1, remember, the n, the thing you're dividing, the m over n, 1 goes into everything. Okay, so you can always just use straight up the factors of these. Not guaranteed to work, but generally, in this case, probably will work. Okay, so if you need to go back and take a look, and I apologize again for my little choking up there with the box. Go ahead and take a look at that, okay? And then I'm going to go ahead and move on to the next one. All right, so you guys have definitely been troopers, haven't stuck it out. Definitely not some easy stuff at all. I'm going to move on to graphs in the coordinate plane, okay? So, we're in the home stretch practically. So, determine the end behavior of a polynomial, and I'm going to stand up for a second because I'm starting to get a little sore myself from having sat through this. To determine the end behavior, you're going to look to the, what's the greatest power of x? It's the degree, okay? So if the greatest power or the degree is an odd number, then the end behaviors are going to be different. But if it is an even number, the end behaviors are going to be the same. Okay, extremely important. Okay, so let's look at this polynomial function right here. So remember, here's what we're looking for. X-intercepts, y-intercepts, and behavior. Here's what I know. It's an even power or odd power. Okay, it's got an even, rather a positive number as leading coefficient. That means the end behavior is going to be opposite, and such that the left points to negative infinity while the right points to positive infinity. Okay, so now I'm going to go ahead and I'm going to find all the intercepts. Well, I know I've got a y-intercept, I don't know, up at 12-ish, and my graph might not be the same as yours, but we're looking for an approximate graph, not necessarily an exact graph. Okay, so now what I'm going to do is I'm going to go ahead and take a look at how do I find the x-intercepts on this one. Let's see. Well, I happen to get lucky, and I happen to plug in my head something for this. So I'm actually going to use the rational root theorem, plus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 12, and I suppose we have a plus or minus 4. I already plugged it into my head. I did 1. I always try 1 just in case. So 1 minus 2, that's negative 1, minus 11 is negative 12, plus 12 is 0. So I'm going to try to do my 1. So I'll try 1 first. So I've got 1, negative 2, negative 11, and 12. Bring down my 1. 1 times 2 is 1, plus negative 2 is negative 1. Negative 1 times 1 is negative 1. That's negative 12. Okay, negative 12 times 1 is negative 12, plus that is 0. So I've got x minus 1 times x squared minus x minus 12. This I can further break down as x minus 1, x minus 4, x plus 3. And now I'm ready to set up my table. My x and my y's, okay? So here's what I know. 1 goes to 0, 4 goes to 0, negative 3 goes to 0. Good start, right? All right. 0 goes to 12, and I have a sense of my end behaviors, okay? So let's set it up. 1, 0. 4, 0, and negative 3, 0. So let's say I do my graph. Maybe I'll put my, so we're gonna go, we'll go up, shoot through it, probably reach some maximum, local max up here, come down, and go to up to infinity. Remember, yours doesn't have to be perfect. Here's what I'm looking for. You have to know, does it pass through or does it bounce? Extremely important. and you have to know the end behaviors. That's what I'm looking for here. So this was not a pretty graph by any means, but I had that down. Next one, let's graph this polynomial function. So the first thing I'm going to do is I'm going to take out the negative. Plus, and I think we talked about this in class as well. Take out the negative, okay? That's extremely, extremely important. Why? Because it's going to be easier to factor. And you're going to have to take a negative out of somewhere eventually. It's going to confuse you down the line, so I like to just take that out now if I can. All right, now I'm going to need to look at things with 54 in it. Now the thing is here, you didn't get as lucky with the 54, so let's take a look. So I've got plus or minus 1, plus or minus 2, plus or minus 3. 4 does not go into 54, right? 4 times, you can get to 52. 4 doesn't go in, 5 doesn't go in, 6 goes in, because 2 and 3 goes in. 7. 7 does not go in, 8 does not go in, 9 goes in. 9 times 6 is 54. Let's see. 10 doesn't go in, 11 doesn't go in, let's see. 7 times 3's got to be equal to 54, right? Because 9 times 6 is equal to 54. Let's see. What times 3 is 54? 18. And 27 goes in. 27 times 2 and 54. So I'm probably not going to plug in 54, right? Nope. Let's see. Maybe I'll do... I don't know. Tough to say just by looking at it. How about we try 2? How about we try 3? How about we try negative 2, negative 3? And if this doesn't work, we'll keep going with it, right? So I've got 1, 1, negative 15, negative 9, 54. So 1 comes down. 2 times 1 is 2. Add to the 1, I get 3. 3 times 2 is 6. Add to the 15, I get negative 9. Okay? 2 times negative 9 is negative 18. Yes. Add to the negative 9, I get negative 27. 2 times negative 27, 54. Add to the 54, I get 0. Look at that. How lucky did I just get there? All right. Now, not the easiest thing in the world. I'm going to have to repeat this, but at least I'm looking down the line of a 27. Right? Looking down the barrel of a 27. Okay? And I'm actually going to be able to recycle these numbers potentially. So x minus 2 is the first. X cubed plus 3x squared minus 9x minus 27. And now I repeat the rational root on the 27. So I'm going to come up here and do the 27. So I've got plus or minus 1, plus or minus 2 doesn't go in, 3 goes in. Let's see, 4 doesn't go in, 5 doesn't go in, 6 doesn't go in because 2 doesn't go in. 7, 8, 9 goes in, and I think 27. That's really all I get. All right, so really quick, I'm going to do a little experiment. If 3 will go into this, then 3 will go into that. Because remember, all the factors of this are the same as the factors of this. So that means if 3 goes into this polynomial, but 3 did not go into this, that means 3 has got to go into whatever is left. So let's see if 3 works, and then we'll go from there. So let's plug it in. So I got 1 times 3 is 3, plus 1 is 4. 4 times 3 is 12, plus negative 15 is negative 13. Negative 13 times 3 is 39. Yeah, 3 is not going to go and doesn't look like. Okay, so I'm going to repeat this, but I'm going to make the numbers a little bit easier for myself at this point. And this might start bleeding into the graph, okay? So what I might do is this. I'm going to bring in a little separate sheet of paper right here. So here's what I've got. I've got 1, 3, negative 9, negative 27. Okay, and then let's look at the factors of 27. I've got 1, I've got negative 1. Okay, unlikely to go into the first one, so probably unlikely to work here. I've got 3, I've got negative 3, and it looks like 3 already didn't work, so I'm probably going to skip 3 and hit negative 3. Let's see, what else do I got? I've got 9, and negative 9. So let's see what happens. So I'll bring my 1 down. 1 times 1. 1 times 1 is 1, plus 3 is 4. Right, and remember we got 4 plus 1 is 4. Plus, that's negative 5. Negative 5 is 5, and that is negative 32. It's not going to work. Okay. Negative 1, let's try it out. Negative 1, so bring the 1 down. That's negative 1. That brings me a 2. 2 times negative 1, negative 2, gives me 11. 11 times negative 1 is 11. It's going to give me 16. Not going to work. What about negative 3? Bring down the 1. 1 times negative 3 is negative 3. 0. Nice. Okay, how did I do that? Well, 0 times negative 3 is 0. Brings down the 9 and the 27. So here's what I've got. I've got the x minus 2 from the original, x plus 3 from this one, and then this is negative 9. So this is x squared minus 9. So that's the same thing as x minus 2, x plus 3, x minus 3, x plus 3, because this is a difference of squares. So it's x minus 2, x minus 3, x plus 3 squared. Okay, that's how you factor it. So I'm going to bring it back, and I'm going to write my factors out. Here's what I've got. X minus 2, x minus 3, x plus 3 quantity squared. So here's what I've got. Off to the left, I'm going to make my little table. And believe me, on a test, you're going to have way more space than I'm giving you here. So I've got 2, I've got 3, I've got negative 3. And I've got 0, which I know goes with now. Be careful. Use the standard form if you can, negative 54. So this is going to give me a 0, this is going to give me a 0, this is going to give me a 0, and I'm going to put a little b to remember that that's a bounce. So I come over, and remember, it's a negative leading coefficient, so I'm pointing down. Okay, it's an anti-field goal. Okay, so here's what I got. 2, 3, negative 3, okay? And negative 54, way down here. Let's say that's that. So here I go, starting down, negative 3, bounce. It's gonna shoot through, shoot back through, and head down. So it's a little m, okay? So remember, on the test, I'm not gonna give you something as difficult as this, but you gotta know a few things. The basic ideas, factoring, including using the factoring table here to get the factoring, identifying the intercepts, knowing when they bounce and when they shoot through, and then building a graph based on that, okay? Now I'm gonna move down to the final one here. Write the formula for a polynomial, okay, that has x-intercepts at negative 3, 0, 2, 0, and 4, 0, and 1, 0, and where it bounces off 2, 0, and 1, 0. What does that mean? So I'm gonna make my f of x equals, so here's how my factors have to start. I have to have an x plus 3, I have to have an x minus 2, I have to have an x minus 4, and I have to have an x minus 1. Okay, you have to start with it like this, and then basically I have to make this an even power because that has to have an even multiplicity to bounce. Then I need to make this an even power to bounce. It doesn't matter what you put here so long as both numbers are even numbers, so you get a bounce and a bounce. Okay, so definitely go back through that, including when I brought in the extra paper if need be, and then I'm going to actually move on to the next part. Alright, you guys are real troopers. Again, as I noted, I'm going to go ahead and I'm going to do this next part about analyzing graphs, okay? So here I go. So this is about the degree and the leading coefficient. If the degree is odd, and by the way, make sure you have a positive and a negative infinity for each one. Alright, if my leading coefficient is positive and the degree is odd, then I'm going to get negative infinity and positive infinity, meaning up, down, okay? Remember, I did that little dance in class. But if the leading coefficient is negative, that flips. So you get a up, down, okay? Now, coming over here, similar thing, negative, even, positive, they both go to positive infinity. Think about like a parabola. And if it's a negative leading coefficient, they both go to negative infinity. So that's some fundamentals about analyzing based on the degree and the leading coefficient. Here I'm going to come up with a function for the formula. And sorry again, HB, about those arrows not being there. I know you would have called me out on that. That's why I put that in there in advance. So this needs to be an even function. It needs to have a positive leading coefficient. Okay, so you can put whatever number in front of it you want, but observe that 1 is a 0, okay, and it bounces off. So maybe put a squared there. And I don't know, it looks like I've got like, I don't know, 1/2. So that maybe I'd put like 2x minus 1, so that would become a half. That's definitely difficult to know. And x plus 1, and that would be my function right there, okay? Why does it have to look like that? Now, knowing this, the total power of x here is going to be 4, because if I was to FOIL this or expand this out, what I would have is, I would have x squared, this would become an x cubed, this would become an x to the 4th, so it'll have an even degree, and because all of the leading coefficients are positive, the number with the highest power is going to have a positive number. In other words, rather the coefficient of the highest power, meaning a positive leading coefficient, meaning up and up. Okay, so that there's definitely a lot of wiggle room there for sure though. Okay, so for this graph, we're going to state the increasing, decreasing, greater than 0, less than 0, end behavior, etc. When I ask you to do this on the test, what I'll say is that it's going to be a lot more clear where those values are. I just want to say that in advance. Okay, so here I go. I'm going to start by looking at this first part, increasing, decreasing. So notice where it's increasing. Let's look to these little areas here, dot, dot. Okay, so here I go. Interval of increasing. Also, here's what I want to note. Notice how these are set up, 2, 4, 6, 8, 10. So I'm actually going to fix mine to make it a little bit easier for you. So if I'm half, this has got to be a 2. Sorry, I misread that. This has to be a 1, negative 1, and this has to be a, so why don't we call it this, make it a little bit easier. Okay, so now I'm going to do the intervals of increasing, decreasing, and greater than 0, less than 0. So I notice a couple things. I'm going to say these are what I call a local min, local min, local min, local max. Okay, so here, intervals of increasing. So it's increasing from here to here and from here to here. So it's increasing from, okay, this is about, I don't know, let's call this, let's say this was negative 1.75. So negative 1.75 to, let's call this like 0.25. And from 1 to infinity. Intervals of decreasing, any other one. So increasing here, increasing here. Decreasing from negative infinity to that first local min. And from 0.25 until we get to 1. Okay, now notice we can stitch the whole domain together. This, then this, then this, then this. Okay, intervals of increasing, decreasing. How about positive, negative? So where is it positive? It's positive here. So it's positive from, well, first it's positive up to the first x-intercept. So it's positive from negative infinity all the way down to negative 2. And it's positive from negative 1 to negative 1 rather to, we've got to be really careful here with our numbers, okay? I'm going to call that actually should be a 2, and this should be a 2. Then it's greater than 0 from negative 1 to positive 2. And actually it keeps going. So you could do this two ways. You could cut it off here because it's technically equal to 0 at that point. And then from 2 to infinity. Okay? Whereas at less than 0, well, there's only one little slice here, and that's from negative 2 to negative 1. Okay, so you just got to analyze here. Maybe do some color coding. So here's where it's negative, and then in a separate color, right, you could do where it's positive. I happen to have a purple pen on me. Here's where it's positive. I think positive and negative sometimes happen to be harder because I'm asking you for x's, but I'm talking about y's. Finally, end behavior. As x goes to positive infinity, and remember the order here doesn't matter, as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to infinity. Okay, finally, multiplicities. X equals 2 has an even multiplicity because we got a bounce. Boop. X equals negative 2 has an odd multiplicity because it goes through. And x equals negative 1 has an odd multiplicity because it also goes through. All right, so take a second look back at this, and again, if you need to look through anything, go ahead, and then I'll move on to the next one. Again, be noting any kind of typos that I've corrected, and they hopefully should be corrected by now in the actual packets that's available on the Binder website. All right, we're in the home stretch now, folks. Believe me, this has been probably as difficult for me to make as for you to watch. Complex roots. So come up with a polynomial in factored form that has these roots, at least these roots, and then convert to standard form. For the sake of this video, I'm going to just stick with factored form, and then I'll let you go from there, okay? So basically, here's what we got. We need to determine every single, like the formula for these ones, okay? So here's what we're going to do. We're going to come through and we're going to try to figure out all of the roots, okay? So we know those already, though. So this needs to be x minus 3, so that 3 makes it 0. Put an x in front so that that will be 0. And now I'm going to do an x squared plus 9 because to solve this, right, the roots are going to be plus and minus the square root of negative 9. And this one's going to be hard, this last one. And technically you're not supposed to have, so here's what I'm going to do. I have to think about this. So I need an x squared in there. And I'm going to need to solve it such that I'm going to need to take the square root of negative 4 ninths. So it's going to be basically the square root of negative 4 ninths. Okay, so how am I going to get negative 4 ninths? Well, I'm going to have a 9x squared plus a 4. So that when I move the 4 over, it becomes a negative 4. I divide, and then I take the square root. Okay, that's not an easy one at all. In terms of determining the real and complex roots, I would say, again, do not get wrapped up, and please, again, super challenge, do not get wrapped up. In fact, I'm only going to really do the jalapeno through with you. Do not get wrapped up in this. It is definitely extremely difficult, okay? And that's all right. Here, again, you're going to have a GCF. I'm going to tell you, again, the ones on the exam, if they're on there, are going to be way not as nitty-gritty as these. All right, so 294, that's not going to be an easy one. So here's what we're going to do. We need to determine all of the roots, real and complex. Okay, so I'm going to start with 294. That's a really big number, right? So basically, we're going to think about the factors there. Well, off the top of my head, I've got 1, 2, and 3, and maybe even 6. And I'm going to start by trying to get that wrapped up here. So I know 1 is not going to work, right? 1 plus 1 plus 43 plus 49, that's not going to work out. How about I try 2? 1, 1, 43, 49, negative 294. Okay, so I bring my 1 down, I get 1. Multiply by 2, I get 2. I add, I get 3. Okay, multiply 3 by 2, I get 6. This becomes 49. Multiply 49 by 2, okay? I get 49 times 2 is, let's see, 98. Over here, I'll do 98 plus 49. Again, you'd have a calculator for that. That would be, let's see, 8 plus 9, 17. And then that would be 14. Look at me, 147. 147 times 2 is 294. I know that because this is 28. That's 14. Add 294, we get 0. So I happen to get lucky on that one. So I've got x minus 2 followed by, so you gotta have faith. You gotta have faith. You gotta believe in yourself here. Because if you just try one, you'll believe it or not, you'll get there faster than you thought. X cubed plus 3x squared plus 49 plus 147. Okay? Now 147, let's break that down. Well, that's still, so we still have a 3 in there possibly. Let's take a look. 7, 8, 12. So we still have a 3, we still have a 1, we don't have a 2. So I'm gonna try, well, let's see if 1 will work. So 1 plus 3 is 4. No, 1's not gonna work. So let's go ahead, and I notice that they're all positive here. Notice that, they're all positives. So I'm gonna start with a negative 3. So I'll start with my negative 3 over there, and let's see what happens. I could be right, I could be wrong. Hoping I'm right. Hoping. So I've got 1, I've got 3, I've got 49, and I got 147. So I bring my 1 down. That will give me a 0. That will give me a 49. And that will give me, right, 49 times 3. 4 times 3 is 12. That will give me a negative 147. And I add, and I get 0. Okay, so here's what I have. I've got an x minus 2. I've got an x plus 3. Okay, I've got an x squared plus a 49. Now, this is supposed to be roots, so I want it, give me the roots, give me the roots. Got to be equal to 0. So, 2 makes that 0. Negative 3 makes that 0. What makes this 0? Well, if x squared plus 49 is 0, then x squared equals negative 49. So x equals plus or minus the square root of 49, which is plus or minus 7i. So our zeros are as follows. X equals 2, x equals negative 3, x equals plus or minus 7i. So the catch is now I'm rolling in i's. And remember that you may have i's, okay, on the exam. So you always want to look out for every single possible solution, real and complex. I'm gonna leave this third one to you just because we've already gone pretty long on this video. So I'm gonna leave this one to you, but here's my hint for you. Look at what you can take out. An x can come out, x in all of them. And a 3 can come out of each one. How do I know? That's divisible by 3. That'll give you 5, that'll give you 4, that'll give you 8, that'll give you 40, and that will give you 32. So everything can be taken, 3x can be taken out of every one of them. I know you can do this, and I'm going to leave that to you. I'm happy to help you before or after school or in another setting, figure that out. And again, remember, this is a super big challenge, right? This is way, way, way more difficult, but if you can do stuff like this, I guarantee you you're going to be in a great place for the test. Okay, last but not least, I'm going to do a little bit of miscellaneous questions, okay? 3 types of this. So there's lots of answers to the first one. Write the equation for a quadratic in factored form that has an odd degree of at least 11, that has n behavior as follows. Both, notice as x goes to positive infinity, fx goes to infinity, okay? Bounces off these intercepts, pass through these, and has 2 complex roots. All right, so here we go. Here's what I know. If it's odd and we have this, the leading coefficient needs to be positive because that's what we know will happen. So let's start by setting up the x-intercepts we know. So I've got x minus 2, x minus 3, x plus 4. Now, you have lots of options. I need a bounce, so I'm going to drop 2's because we need an even multiplicity for a bounce. Now, I need to pass through, so I've got x minus 1 and x plus 3. Keep those odd for now. And then I need 2 complex roots, so I'm going to make this x squared plus 9. Okay, because that will have roots of this. Now let's look at this. So 2, 4, 6, 7, 8, 9, 10. Here's what I'm thinking of. As I multiply through, what I know is that these x's are going to determine the degree. Okay, and if I add the x's powers up, 2, 3, 4, 5, 6, 7, 8, 9, 10, that is going to go ahead and give me an degree of 10, right? 2, 4, 6, 7, 8, 9, 10. Here's what I'm going to do. I'm going to go ahead and I'm going to make, I need a degree of at least 11. So maybe I'll take one of these 2's and make it into a 4. And now I have 2, 4, 8, 9, 10, 11, 12. I need an odd end behavior. Okay, so it's going to present another challenge. Maybe I'll go ahead and I'll square this one. 2, 4, 5, 6, 7, 8, 9, 10. All right, 4, 5, 6, 7, 8, 9, 10. You know what? Let's double count this. 2, 4, 8, 9, 10, 11, 12. Aha. So here's what I can't do that, right? So this is going to be a challenge, definite challenge. May not be possible to do this based on the fact that we have to have an odd degree. So here's what I'm going to do. Maybe I'll just add another x-intercept on there. Maybe I'll just tack an x in front of there. So now I have an x-intercept of 0. All right? But here's the thing. I need an odd degree of at least 11. Let's check my degree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's got a degree of 13, because this is the issue, right? If I have 1, 2, 3, 4, 5, 6, 7 roots, right? Then if I have to make those even multiplicity, that's going to be a challenge. But again, notice leading coefficient will be 1, giving me an end behavior pointing up, and that's what we'll do. All right, not an easy one, but the big idea is that I want to work backwards, okay? I want to start from the roots and go back to the original function. Okay, on the eventual packet, I may add this on my corrected version to maybe take away one of those roots, or in other ways modify it to make it more straightforward. All right, on the quadratic plane, on the coordinate plane, sketch the graph of a quadratic that has the same end behavior on both sides. So we can't call this a quadratic. We're going to actually call this a polynomial that has the same end behavior on both ends and has these x-intercepts. So I have 2, -1, and 3. Okay, already can't be a quadratic because it's got to have at least 3 roots. Okay, you got a lot of options. You need the same end behavior on both ends. So I need to have something be squared because I'm going to need a bounce because I'm going to start here. Let's say I start here. How am I going to end here? Right? Hard. So I'm going to have to go through, okay? I got to bounce somewhere. So why don't I make my y-intercept here and come through, bounce, come up, go through, go through. Okay, that's the idea. It's got to go up in both directions so that we have that. Lastly, on the coordinate plane, sketch the graph of a quadratic that has opposite end behavior, a negative leading coefficient, and roots of the following. And this is, again, is not a quadratic. This is a polynomial. Okay? So I've got -2, +4, 0, and 3. Okay? I need opposite end behavior, but I have to have a negative leading coefficient. Okay, what does that mean? Well, that means that not only that, but I have to have this one will start up here, and this one will go down there. That's what a negative leading coefficient will do. And I've got to get down there in the end. So I need to go whoop, doop, doop. Uh-oh, I'm going to need another bounce somewhere. So how about we have it go through, bounce, go through, go through. So that would be something that looks something like this, right? We would have x squared right? We'd have x plus 2. We'd have, let's see, x minus 3, x minus 4. So 2, 3, 4, 5, odd. Maybe I stick a negative number to make it a negative leading coefficient, and so on and so forth. All right, so lots of this video. As you can see, there's definitely some things I'm going to have to call our attention to in terms of corrections. I would expect that either I will explicitly tell you the corrections and or I will make those corrections in the official packet. This has definitely been a very detailed, definitely very drawn out video, and I appreciate and I hope that you've looked through some problems to see where you can do this. Remember, please reach out to me, come and see me for extra help. Definitely ask me questions anytime, and remember, you can do it. All right, so best of luck, folks. Stay positive. Look out for my corrected version, and have a wonderful day.